Hello, everybody. This is lecture 4, and it's in many ways a companion lecture to the lecture number 3, which we just finished, which is the central tendency. And so we're still in descriptive statistics, so we're describing our samples data. We're sort of summarizing what it looks like for somebody looking at our research, but we are not testing any hypotheses. All we're simply doing is just describing what our sample looks like on a certain variable. And we did the last lecture on central tendency, and now we want to sort of talk about variability. And I kind of want to, let's just start this with a more simple thing than what's provided there. So let's snip this. So remember, central tendency is we cared about the bulk of the data, where most of the data were, or where the data is centered. Variability is the other thing that we're sort of curious about. So making a very rough distribution here. Remember, central tendency cared about where the bulk of the data were. Variability cares about how far things are spread out. So if the bulk of the data are here, how far are the scores spread out from the center of the data? So variability is how far are the scores from the center of the data. And I'm going to just, oops, I don't like that ruler. Looks very much like the eraser. And we can contrast two different distributions to sort of basically say why we're doing this. So let's say we have something that looks like this. The center of our data is here. There's not a lot of variability. There's a lot of scores that are very close to the center of the data. A lot of scores very central to the close to the center of the data. There's a few that kind of stretch out this way, a few that stretch out this way, but there's a lot very close to the data right there. But if we have a distribution that looks like this, and the center of our data is here, the scores are a lot more spread out. There's a much bigger spread from the center of the data. I hope you can see that kind of in this rough illustration. So this one would have smaller variability. Why? Because a lot of the scores are very close to the center of the data, so there's not much variability. They're not spread out. There's a lot of them in the middle here. They're not spread out. So it would have a lower variability. This distribution has a higher variability. Why? Because a lot of scores are away from the center of the mean, especially in comparison to that. So this would have more variability. People in this sample, in this distribution, a lot of them are quite some distance from the center of the data. So obviously the center of the data, and maybe with these two distributions, because they're pretty normal, we would be using the mean, and maybe the means were the same. So we could have the same mean in these two distributions, but you can see by just having the mean, we don't really understand what the data look like. We need that sense of variability because they look quite different. So let's say they have equal means, but the variability is very small here, so there wasn't a lot of spread in the scores. Here, the variability is very high, so there's a lot of differences between people. Less differences between people, more differences between people. So variability is crucial also in terms of our descriptive statistics because it gives us a better view of what the data look like. You can freeze on this if you want to read through that. This is what we're covering. So basically, this is what we've been talking about. And just like the central tendency, there's several ways that we can talk about variability. So variability is essentially done one of two ways. You could talk about the difference between two scores. And we've actually already done that. If you remember in our frequency distributions lecture, one of the first things that I started talking about in terms of describing the frequency distribution was to describe the range. The range was the difference between the highest score and the lowest score. So, for example, I believe it was the average amount of sleep per night during the first week of the semester. There was a range that was 11 was the highest amount of hours of sleep per night, and 4 was the lowest average hours of sleep per night. So actually the range would be 11 minus 4, so the range is 7 hours, and that's all that's saying is that there's 7 hours difference between the person who had the most sleep minus the person who had the least sleep. So the highest score minus the lowest score. So the range that we've talked about is one of those approaches that uses the difference or distance between two scores. Then another approach that we would take is the distance from the mean. And so I kind of did that in the thing I just drew for you just now, those two distributions. I sort of drew the mean. I drew the central tendency measure, which we had a basically normal curve, so that was the mean. And I drew those arrows, and I was sort of showing how far those arrows, the scores, were from the mean. And so this approach does that. This approach finds the mean, and then it looks at all the scores and how far those scores are from the mean, and essentially adds those distances together and divides it by the number of scores. So it's an average distance from the mean. So that's another approach, is distance from the mean. And that's the one that's actually one that we use most in psychology because it's more accurate and more telling because it counts for all the scores. The first approach, which is the difference between two scores, is a little bit more crude because all you're looking at is the variability between two people. The second approach here is the distances from the mean, is the variability of everybody from each other, essentially. And again, this is a descriptive statistic. We are not testing hypotheses. We're just describing what our samples data look like, what our samples distribution of the data look like. And this is similar to the one I just drew for you. The one on the left would have higher or lower variability. The one on the left has lower variability. The scores are much closer to each other. How about the one on the right? Higher or lower variability? Well, you should know now it's higher. So one on the left is lower variability. On the left, people are close to each other. One on the right, there's higher variability. People are farther away from each other. And here we have 4 measures of variability, but really there's really only 3 because the last 2 are the same thing. They're just slightly different. So we have range and interquartile range. So actually these first 2 things, they are ranges, and they do take that first approach of the differences between 2 scores. And then variance and standard deviation take the second approach, which is the distance from the mean. And variance and standard deviation are essentially the same thing. When you know one, you know the other. And we'll get into the specifics about that in a little bit. Range is super simple. We've talked about it already. It's the difference between the highest score and the lowest score. That's it. It's not a great measure of variability because you're not looking at all the data. So it's not really used much. Sometimes people report it, but people just report it because people are curious about the highest and lowest score, but it's not something that you do a lot of analysis with because you don't really care that much about that. You might just be sort of curious what the range of scores were. Interquartile range is a little bit more complicated. And the interquartile range, what you basically do is you're dividing your distribution, your sample, into 4 parts. So quartiles, 4, quarter. And what you're simply doing is, and I think I'm going to draw it before we get into all those little things that are on there. And so we're just dividing our sample into quarters. And when we do the interquartile range, it's pretty easy, typically. So here's our lowest score, and then here's our highest score. So here's our highest score, here's our lowest score. And remember, we've already covered the concept of median. So at our median, we're at the 50% mark, right? So 50% of the scores are over here. I didn't want to do that. It was an accident. Oops. Make sure I'm erasing it. So 50% of the scores are above the median, 50% are below. So we already know how to find that. So when we do the interquartile range, that's usually what we do is we take the low score, high score, we array them from left to right. We find the median. The median is where 50% are above, 50% are below. And then what you typically do then to find the interquartile range is you want to find the median of the upper half, and you do it the same way. You just simply take the scores here, starting here at the median to the highest score. Then you find the median of the upper half. The median of the upper half obviously would be at the 75th. We would call it percentile. This is 75th percentile because 75% of the scores are below this score. And of course, conversely, 25% are above it. So this is actually called Q2, quartile 2. This is called Q3. This is Q4. So again, we're just dividing the scores into quarters. This, by the way, is Q0. The lowest score is Q0. And then to find the interquartile range, we need to find the median of the lower half. So we can do the same thing. We can take the scores from the median to below. So there's 50% of the scores there. If we find the median of that, it should make some sense. So we have 75 percentile, 50th percentile, 50% of the scores are below this. This is a 25th percentile. 25th percentile, 25% of the scores are below it, 75% of the scores are above it. And so this is Q1. And so just to sort of go through this, 25% of the scores are between the low score and Q1. 25% of the scores are between Q1 and Q2. So 25 plus 25 is 50, you can see here. And then 25% of the scores are between Q2 and Q3. So 50 plus 25 is 75. And then there's 25% of the scores between Q3 and Q4. So we've divided up our samples data into 4 equal parts with 25% of the people in each of those 4 parts. What is the interquartile range? The interquartile range is actually, you take the score at Q3, so whatever score is here at Q3, and then you subtract the score at Q1. So that's the middle 50% of scores. That's the difference in scores for the middle 50%. So there's 25% here, there's 25% here, and these are the ones in the middle. So it's the middle 50%. So for this interquartile range, which we sometimes say IQR, we typically use the interquartile range when we have skewed data. So if you have a really skewed distribution, the IQR is nice because we'll find out is that the other measures that use the average distance from the mean, so it's just like a average, for central tendency, the mean, if you remember the average, the mean for central tendency, we didn't want to use that for a skewed distribution because it got pulled too much towards the extremes. And same for this one. If we tried to do an average distance from the mean, which we'll talk about in a little bit, extreme scores would throw that off. And so when we have a skewed distribution, we typically would like to use the IQR because we only look at the middle 50%. So if there's skewed scores either higher or lower on this distribution, and then that throws off other measures of of variability, all we do in IQR say, well, let's look at the middle 50% because there's not so many extreme scores there. Let's just look at that middle of the distribution and see how far Q3 differs from Q1. So that's what the IQR is. That's conceptually what it is. And actually, that's how you do it too. And we'll actually look at how to do it here. So I already just talked about that. So we're dividing our samples data into quarters with 25% of the people in each of the quarters. And the interquartile range is Q3 minus Q1, which is the person at the 75th percentile, where 75% of the people are below them, 25 are above. And then the 25th percentile, where 25% of the people are below them, 75% are above. So if you actually take 75th percentile minus 25th percentile, you'll see that you'll have 50% of the scores. So it's that middle 50% of the scores, the difference between the score at 75, score at 25, take that difference, it's the middle 50%. So again, this is something that's desirable when we have skewed data because skewed data has outliers, has extreme scores, and it would throw off other measures of variability. So here's what we simply do, and I already sort of talked about this. So here's some real data. So step number one, array the data from higher to lower, left to right, find the median. Right here, the median is 98. Half the scores are above, half the scores are below. I'll count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 above it, 5 below it. So now we have the median is there, and then we don't use the median, so we just take this. We have 103, 108, 116, 121, 234. So the median of the upper half is 116. So 116 is actually Q3, the 75th percentile. They call it upper quartile here. Then we do the same thing. We take the lower score. So we go from the median, but we start here with 93. There's 5 scores here. The score in the middle of those scores is 53. So 53 is Q1. So the interquartile range is Q3, which is 116, minus Q1, which is 53. So that's relatively easy. If you have questions about that, you can come to the Zoom sessions. We can work out other ones, but I think that's pretty straightforward. I also want to cover this thing called a box plot. A box plot is a kind of a very simple way that you can quickly, with a small amount of data, represent the distribution. Actually, with a large amount of data, you can do it with this too. But basically what you do is you have your numbers down here. The numbers are not exactly here, but you can just see that we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, da, da. The numbers are down there. And you actually just graph out those quartiles. So when you do a box plot, I recommend starting with the highest number and the lowest number, and then you put this little, we call it a whisker there. So the lowest value is here, the highest value is here. So remember, we're going to divide it into quarters. So just like our interquartile range, find the median. I would just put the line of the median first. Then you find Q3, the 75th percentile score. Put a line there for Q3. And then Q1, which we've calculated from the IQR, draw a line for Q1. And then you box in the middle 50% of the scores with the median line there. So you can see here we have 25% here, 25% of the scores here, 25% of the scores here, 25% of the scores here. And then for the middle 50th percent, which this is the interquartile range, this box is the interquartile range, put the median, draw a line for the median, and then we just connect the points. And so this actually tells us what kind of distribution we have. It might seem tricky at first, but what you want to look at is you want to look at the distance between the quarters. So the first thing that my eye goes to is the middle 50%. So it looks like it's stretching this way. Then you can actually then look at these whiskers, and are one of these whiskers bigger? This one looks a little bit smaller, this one looks bigger, so it looks like things are pulling this way and pulling this way. There's longer scores here. What this suggests to me is that this looks like a positively skewed distribution because things are being pulled to the right. So again, this looks like a positively skewed distribution because things are being pulled to the right. You can see that this box is being pulled to the right. This line is being pulled to the right. Things are being pulled towards higher scores. So to me, that looks like a positive skew in terms of the distribution. Let's look at this one. So let's say that we look at the pulse rate per minute for 40 people, subjects or people. And so we plot this out, so we divide it in quarters. So we have 25% of the people are here, 25% are here, 25% are here, 25% are here. What kind of distribution does this look like? Pause the video and give your answer. Okay, hopefully you've had the answer. I think it looks skewed. There's a little bit of a skew here, but it might not be like too extreme, but this should be really obvious. There's a lower sort of whisker here, and there's a pull. There's a big pull going this way. So if you have a pull going to the right, to the highest numbers, that's a positively skewed distribution. This probably makes some sense. There's some people who are like little gerbils or whatever, and their heart rates are really high. And there's probably a certain limit here. You probably can't get down below a certain heart rate unless you're some sort of big yoga guru or something like that who can control their physiological stuff. There's probably a limit how low you can go and still be living. And so it probably makes some sense that there'd be a positive skew to these data. Let's look at another example. Now I'll make this a little bit more complicated. So we have two classes here. We have Mr. Scarlett's class and Mrs. Plum's class. And we have box plots for them. With all the box plots, we have 25%, 25%, 25%, 25%, 25%, 25%, 25%, 25%. So just looking at these box plots, which teacher do you think is the better teacher? And again, please pause the video and answer this. Okay, you should have answered this already. If you haven't, do it. So this is actually pretty subjective, but I like this question. So, to start with, you can see that the highest score is the same for both of them, but it looks like Mrs. Plum has lower scores. And you can actually see that 25% of her students score well below the lowest 25%. So the lowest 25% for Mr. Scarlett is here. So Mrs. Plum has a lot more students doing worse. These are pretty low scores. So 70, so for Mr. Scarlett, it looks like, actually it's above 70. So for Mr. Scarlett, 75% of the people are getting above 70. So 70 is here. And so we know there's 25 plus 25 plus 25. So 75% of his students are getting above 70, which would be passing. Mrs. Plum, we don't know exactly, but we know that there's more than 25% who are getting below 70. And it's a very negative skew here. Mr. Scarlett, there's a little bit of a skew here, but the skew is really here. There's more of a positive skew. In terms of students who are getting higher scores, Mrs. Plum seems to be doing a little bit better. So for the top 50%, her top 50% is getting above 84. Mr. Scarlett's top 50% is getting about 78. So the top 50% of students are doing much better in Mrs. Plum's class versus Mr. Scarlett's class. And then also I'm curious about the median. The median is much higher. Well, that's the top 50%, so we just talked about that. The top 25% is similar. So the top 25%, just like the top 50%, are doing better in Mrs. Plum's class. Her top 25% is getting above 92. Mr. Scarlett's top 25% is getting, looks like 85. So a bit of a mixed picture. So students who are lower achievers in terms of whatever grades these are based on or test are doing more poorly in general in Mrs. Plum's class, but the students who are higher achievers are doing better. Mr. Scarlett's, the lower achievers are doing better. Whoops, sorry about that. Doing better than Mrs. Plum's class. However, the higher achievers are doing less, have lower scores in Mr. Scarlett's versus Mrs. Plum. So this is a pretty complicated interpretation. I hope you were able to follow it. So for students who need more help, I'd say Mr. Scarlett looks great. For students who need less support and might be ready to learn whatever is being taught in this class, probably it looks like Mrs. Plum is a better teacher for them. So it sort of depends. I mean, my preference would be, I guess, Mr. Scarlett, in the sense that I feel like there's so many people being left behind in Mrs. Plum's. And these students are probably going to be fine anyway in terms of their learning. So that's how we can use box plots. So box plots are really interesting ways to look at distributions and to judge the distributions. We can compare distributions to make judgments, just like this example. And it reinforces that whole thing about interquartile range is dividing things up into quarters and looking at the middle 50%. So remember, interquartile range is difference between Q3 and Q1. That's represented in this box in the middle. Sorry about that. Box in the middle. Okay, let's get to things that need more calculation. And so the first two things we did was range and interquartile range. Those are both based on the difference between two scores. Range, highest score minus lowest score. Interquartile range, the score at Q3, the 75th percentile, minus the score at Q1 at the 25th percentile. So the other approach, if you remember, is looking at the distance from the mean. And what I'll say is the distance from the mean, it will be an average. So what we're going to do is we're going to find the mean, and then we're going to look at every score and see how far it is from the mean and look at how far that distance is, and then we're going to add those distances from the mean together for all the scores, and we're going to find the average. So this is what I was saying, is that in skewed distributions, we don't want to take the approach of standard deviation and variances, because just like the mean, like any average is going to be off when you have extreme scores. Same for this one. For the standard deviation and variance, if we have extreme scores, they're going to have a lot of distance from the mean. It's going to make the variation, the variability, look larger than it really is, because it's pulling the variability up way high because of those extreme scores, just like the mean was pulled higher or lower towards the extreme scores. So typically we want to do standard deviation and variance with distributions that are roughly normal curves. Okay, so let's go ahead and do this. So this is the most common measure because it's more precise. Remember that the interquartile range and range are only based on the difference between two scores in your whole sample, only two people. So standard deviation and variance is better because we base this number on everybody's score, everybody's distance from the mean, and we take an average of that distance from the mean. Okay, here's a formula. Don't panic. It's not too complicated, and we will calculate these things in a second. So this little s right here, that's the standard deviation for a sample, by the way. We'll get into the symbol for population later. But that little s there, that's the standard deviation for the sample. And so the standard deviation is this whole thing that's a square root. What's inside there? So what this is telling us, and I'm just going to sort of talk about what it's telling us. What it's telling us is this first part. Let's look at the parentheses first. What it's telling us is take every score. Xi means every score. So for every score, we're going to take the mean, the distance from the mean. So take the score, subtract the mean, square that difference. And we're going to do examples, so don't worry. If you aren't following this, we'll have real numbers so you can follow this. But all it's telling us is for every score, subtract it from the mean, and then we're going to square it. And then we're going to add those things together. So for every score, find how far it is from the mean and square that difference or square that distance. And then once you have that for every score, that distance from the mean squared, add those together. So when we do the add them together, this highlights why we are squaring things. Why are we squaring things? Because if we don't square it, square the distance from the mean, we're going to come up with 0. I'm going to sort of draw something here. Oops. I'll just double check that I have this thing ready. So here's our mean. Our mean is here. And so we're going to take every score and find how far it is from the mean. So we're going to take every score and find out how far it is from the mean. And we'll do the same thing over here, and it's symmetrical. It's a normal curve. So we're going to find the distances from the mean, and we're going to add them up. But we have to square them first. Why do we have to square them? If we didn't, so let's say there's a +1 here. It means there's going to be a +1 over here. I'm sorry, -1. Let me erase that. So over, I don't want that. So over here, we're 1 above the mean. There's going to be 1 below the mean right here. This is just as an example, but there's going to be something that's 2 above the mean. There's going to be something that's 2 below the mean, because here's the mean, and these are lower scores, and these are higher scores on the right. That's really annoying with this laptop. There's going to be, there's going to be a score that's above 3 above. There's going to be a score 3 below, etc. So in that formula that I just showed you, if we didn't have that square, what would you do if you added all these together? If you added all those together, you're going to come up with 0. Because -3 + 3, -2 + 2, -1 + 1, they're all going to cancel out each other. And so in the end, you're going to have a variability of 0, and there's not a variability of 0 here. So we have to square these things. So if we square these things, this is a 9, this is a 4, this is a 1, this is a 1, this is a 1, this is a 4, this is a 9. So now we can add them together. If we add those together, there's actually a number there that's not 0. So that's why we're squaring it, because if we didn't square it, the things that are above are equal to the things below the mean, and we would end up with 0, and we don't want that. We need a number. So that's the top part of the formula. The bottom part is pretty easy. Once you've added all of those squared distances from the mean, we are simply going to divide it by n minus 1. Why is it n minus 1? Because when we did the average, when we did the mean, it was n, just simply n, the number of scores. Well, without getting into complicated stuff, n minus 1 just makes an adjustment. So there's these statisticians that sit around and run what they call simulations with a bunch of different numbers, and nowadays with computers you can do millions within an hour. And what they find is if you just have n, the standard deviation is essentially off, is biased. So when we do n minus 1, it's called a unbiased estimate, because with our statistics, all we're simply doing is making an estimate of what the population value would be. So for standard deviation, we just say n minus 1 because it corrects for some mathematical bias. And I really don't want to talk more about it because I think that gets into minutia that you don't necessarily need to know. But that's why it's n minus 1. It's something we have to do mathematically, so the number is more accurate for standard deviations. And then once we take the sum of the distances from the mean and squared, we divide that by n minus 1, the number of scores you have minus 1. Once you have that number, then you take the square root. By the way, this number inside the square root, so without the square root, if you just did this thing without the square root, that would be the variance. So that's why I was saying that the variance is the same thing as standard deviation, because if you know the standard deviation, you square that to get the variance. If you know the variance, which is the stuff inside the square root, so if you know the variance, you take the square root, you get the standard deviation. And don't worry if that's not quite catching yet. Well, we'll talk about it more. So here's an example. So if the formula was a little bit confusing, let's look at an actual example. So we have a pretty small sample here. We have 5 people. Their scores are 2, 3, 5, 7, and 8. If you calculate the mean, add those scores up, divide it by 5, the mean is 5. So let's do the first part. Remember that we have to take every score and subtract the mean. Remember the first part says take every score, subtract it from the mean, you square that, and we're going to end up adding those things together. So we take every score, we have 2. 2 is the first score, we subtract the mean of 5. 2 minus 5, we need to square that, but let's just say 2 minus 5 at first. Remember, we have to add these things together. So the next score, so plus, and then the next score is 3. We have to subtract the mean. 3 minus 5. 5 is always the mean. We're going to square that difference. Then we're going to add 5. 5 is the next score. 5 minus 5, square that. Plus 7. 7 is the next score. 7 minus the mean, 5, square that. Plus 8. 8 is the next score minus the mean, which is 5, square that. So if we take 2 minus 5, that's negative 3, correct? Negative 3 times negative 3 is 9. See, this is why, again, we square it, because we want all positive scores, because if we didn't, we'd end up with 0. 3 minus 5, so that's 2. 2 times 2 is 4. 5 minus 5 is 0. 0 times 0 is 0. 7 minus 5 is 2. 2 times 2 is 4. 8 minus 5 is 3. 3 times 3 is 9. So now we have all of the squared distances from the mean right here, down here. 9 plus 4 plus 0 plus 4 plus 9. So remember, add all those squared distances from the mean. Add them. That little sigma, add. So now we have 26. So 26 is this number, the top number right here. So 26 is the top number, and all we have to do now is take n minus 1. Well, what was n? N was 5. We had 5 scores. So 26 divided by 4, 5 minus 1, 4. So 26 divided by 4 is 6.5. That's the variance. Remember I told you that the inside part is the variance. So if you know the variance, take the square root, you'll get the standard deviation. If you know the standard deviation, square it, you'll get the variance. So 6.5 is the stuff inside, is the variance, and all we have to do is take the square root. So take the square root of 6.5, that's 2.55. Now we have our standard deviation. That's our standard deviation. So remember, if you know the variance, take the square root to get the standard deviation. If you know the standard deviation, take that squared. You can check it. Take 2.55 times 2.55, you're going to end up with 6.5 with maybe some rounding error. So relatively easy. So this thing, when you see it, you think, oh my gosh, all it's telling you is first take every score, subtract the mean, square that difference, add those things together, divide it by n minus 1. Once you have that, take the square root of it. So for every score, subtract the mean, square it. Down here's the squares. Add those together. Then you subtract it with n minus 1. And then once you have that, you just take that square root. So just like with everything in statistics, it might look complicated at first, but it's just a matter of just doing the steps. Step 1. Step 1 is take the difference between each score and the mean. You're going to square that. You're going to add those together. That's step 2. Once you've added those together, step 3 is divide it by n minus 1. Then step 4 is to take the square root of that number. So it's relatively simple stuff. It's just make sure that we do all the steps. And that's what the formula is. The formula, like I told you earlier, might look complicated, but it's just telling you what to do. First thing to do is this stuff in the parentheses, including the squares. Then you add them. This is telling you to add them. Then it's telling you to divide that by n minus 1. Then it's telling you to take this whole thing and then take the square root. So the formula might look complicated because of the symbols, but the formula is the recipe. Add the sugar, add the flour, add the chocolate, bake it, you're going to have a cake. In this case, it's a cake you can't eat, standard deviation. So let's do some. So I say here, give me some data. In class, in a face-to-face class, I have people give data, and then we go ahead and do it. I'm going to give you the data. Remember that this is the formula for standard deviation. Oh, just wait a second. We're going to have an example later. Yeah, I want to do this because I'll do this a little bit later. Should probably take this slide out, but there is an example later, so sorry about that. So let's think about kurtosis before we do the example of the standard deviation, because I want to do something within that example that illustrates something, another concept that I want to talk about. So sorry about that rougher transition. So we'll get back to standard deviation. I will give the formula again. Let's just review something we know already, which is kurtosis. So remember the 3 types of kurtosis? We had the leptokurtic, we had the mesokurtic, and we had the platykurtic. And they're right here. So the blue is leptokurtic. Remember, it leaps up. Meso's in the middle. So the one in the middle is meso. And platykurtic is the one in red. So it's like a platypus pushed down. So leptokurtic has the smallest standard deviation, because remember, the leptokurtic is leaping up and it's pulling all these scores into the middle. So the distance from these scores to the mean is pretty small in a leptokurtic distribution. Mesokurtic will be in the middle, but then platykurtic, remember, we're pushing it down, and because we're pushing it down, the scores are spreading out more from the mean. So a platykurtic will have a higher standard deviation. Leptokurtic will have less variability. See, everybody's in the middle here. So it's going to have a lower standard deviation. Platykurtic, we're pushing it down. People are spread out more. There's more variability, so there's going to be a higher standard deviation. And we can actually look at this. So meso's in the middle. So the blue Leptokurtic has a standard deviation of 0.7. The platykurtic one has a standard deviation of 1.5, so more than twice as much variability. So kurtosis is also another way of sort of talking about variability. Lepto, things are closer together, pulled together, lower standard deviation. Platykurtic, things are pushed down, people are spread out. More spread out, there's a higher standard deviation. So I think this might be the final concept we're going to talk about. This is why I want to do the example later, is to introduce this concept. The concept is the sum of squares. What is the sum of squares? I think I'm going to highlight this thing. Oops. Keep on forgetting I was able to put it into the tool bar there. I'm going to cut this is our standard deviation formula, and I'm going to make it bigger. It's a little fuzzy. Sorry about that, but you can still read it. What is the sum of squares? Sum of squares is this part of the formula. It's the top part of the formula. Why is it called the sum of squares? Well, there's squares here, right? So this little sum, that means add. So sum, and what are you summing? You're summing the squares. The squares are, you take every score, you subtract the mean, and you square it. This thing is the sum of squares. We say SS, sum of squares. Why am I talking about this? The sum of squares is used often in statistics talk. So if you ever hear anybody say sum of squares, that's what exactly it means. It's the top part of the standard deviation formula, which is the sum of each score minus the mean squared. That's the sum of squares. And so that top part of the formula is what we call the conceptual formula. There's also a computational formula. What I'll say is, don't worry about this too much right now. Put this in your pocket. Don't worry about it. We're going to talk about it a lot more later, but I just sort of want to highlight that you can compute it more quickly with larger sets of data. But for now, we're going to stick with the conceptual formula, the definitional formula. So just remember the concept of sum of squares, which is this thing on the left that we've been talking about. But when we get to the sum of squares later in this semester, we have quicker ways of computing it. So this is just something to highlight an issue that we are going to talk about later. But the concept of sum of squares is important to kind of start getting into our brains. And so we aren't going to get into this right now. This is more useful later in the semester. So you can skip that slide that I just went over. But the thing is, if we actually computed this with that formula, it comes out to the sum of squares is equal to 26. Why do I have that sum of squares 26? Let's go backwards in time. That's the data that we had earlier in our example. Do you see 26 on this slide? Yes, you do. Where do you see it? You see it right here. If I can get my cursor going. 26 is right here. Where did 26 come from? We took the sum of squares. We took every score, subtracted the mean, we squared it. We added that together. So when we added this together, that's 26. So sum of squares is the upper part of the formula in the square root in the standard deviation formula. So it's a number that we're computing on the way. So actually, when we're doing the standard deviation, we're finding the sum of squares first. Then we find the variance, and then we find the standard deviation in the end. So one of the reasons I'm going into this not only is the sum of squares something that is talked about often in statistics, but I want you to realize that in statistics, often things are connected with each other. So, you might think, oh my gosh, he just told me three things: sum of squares, variance, and standard deviation. Well, actually not. They're actually kind of the same thing. The sum of squares is this top part. It's just kind of the distance from the mean for all the scores taken together, added together. Well, Yeah, that's nice to know the sum of the distances from the mean, but we need to take an average for it to be useful. So the average is the variance. But this is actually pretty large and doesn't really tell us what's going on. So we have to take the square root to get the standard deviation. It's something that's a little bit more meaningful, and we'll learn the meaning later in this semester. But really, these are three of the same things. They're basically the same thing in many ways conceptually. Distance from the mean, well, if you add them together, the squares of those distance from the mean, that's the sum of squares right here, 26. If we take an average without adjusting it, it's the variance. If we adjust it with the standard deviation, or I'm sorry, the square root, that's the standard deviation. So there are really three things that are the same thing. So in statistics, one of the games that we will solve is things are a lot more connected than they seem. So I realize that this is only the fourth lecture, so this might not be clicking quite yet, but I do want you to realize that these things are connected. Okay, so let's go ahead and do an example. Yep. So here's some data. So I'm going to have you do this. So I'm going to give you these data. I'm going to have you calculate the standard deviation. And I think I'm going to change this. I want to highlight the sum of squares and variance on the way. Okay, so this is an example that, so in class, what we're going to do is I'm going to have numbers, and I'm going to give you those numbers as examples. And I want you to solve them on your own. And then I'm going to review the answers after you've solved them on your own. So here's our data. We have 6 people. There's the data on the top line. I gave you the mean. I just wanted to double check it, but you can double check it. But I have confidence that you can find the mean pretty easily. So the mean is 11 for these data. So I want you to calculate the standard deviation using the formula, which is not there. It's right there. So use that formula for the standard deviation that we had before. And then on the way, because remember, on the way, we're going to calculate the sum of squares, and we're going to calculate the variance. So we want to get the standard deviation, but also highlight the numbers for sum of squares and for variance on the way. So pause the video now and solve this on your own, and then I'll do the solution when you're done. Okay, here's the solution. So the top part is the formula. I just cut and pasted it just right there. Remember, the first thing that we have to do is we have to take every score, subtract the mean, and square that, and we're going to add those things together. So here's our scores. Our scores were 7, 9, 10, 12, 13, 11. So for every score, we subtracted from the mean 11. 7 minus 1, 9 minus 11, or sorry, 7 minus 11, 9 minus 11, 10 minus 11, 12 minus 11, 13 minus 11, 15 minus 11. So we're just taking every score, number 7, 9, 10, 12, 13, 15, and subtracting each of those scores from the mean. The mean was 11. And then we have to square those differences. So 7 minus 11 is 4. 4 times 4 is 16. 9 minus 11, that's 2. 2 times 2 is 4. 10 minus 11, difference is 1. 1 times 1 is 1. 12 minus 11, 1. 1 times 1 is 1. 13 minus 11, that's 2. 2 times 2 is 4. 15 minus 11, 4. 4 times 4 is 16. So we add those together. Remember, it says to, in this formula, it says to take every score, subtract the mean, square that, but add them together in the end. So we add those together and we get 42. 42 is the sum of squares. The sum of squares is this top part. What are the squares? The squares are each score minus the mean, square it, and then add them together, sum of squares. So 42 is our sum of squares. Then we have to take 42, we have to subtract that from n minus 1. N was 6. 6 minus 1 is 5. So 42 divided by 5 is 8.4, and I'm going to put this here. That is the variance. So remember, all that stuff in the middle of the square root is the variance. 8.4 is the variance, and sorry about that. This thing is off. I'll correct it. So now we take the square root of 8.4. The square root of 8.4 is 2.09. That is the standard deviation. So again, if you know the variance, take the square root of the variance, get the standard deviation. If you know the standard deviation, square it, and you'll get the variance. So hopefully this formula, which looked complicated at first, is pretty easy as long as we take those steps. Step 1, take every score minus the mean and square it. Add them together. That's step 2. Step 3 is once you have that, sum of squares, divide that by n minus 1. So that's step 3. That gets our variance. Step 4 is take the variance and take the square root of it to get the standard deviation. So it takes 4 steps, but they're not complicated calculations. So hopefully that's relatively clear. And we'll talk more about standard deviation later in the semester, how we can kind of look at it. But right now, we just know that the lower our standard deviation, it means that there's less variability. So a small standard deviation means less variability. Things are closer to the mean. So remember that the standard deviation is essentially the average distance of the scores from the mean. So a lower standard deviation means that scores are closer together. There's less variability. A higher standard deviation means that scores are more spread out. There's more variability. People are farther apart. We've already talked about this. So the variance is the standard deviation squared. If you know the standard deviation squared, you'll get the variance. When you know the variance, take the square root of the variance, you'll get the standard deviation. By the way, I mentioned that we'll talk about this later. The symbol for standard deviation for a population is this little curly Q guy, sigma, I believe it's called. The little curly Q guy. So the little s, I'm sorry, this is standard deviation. So the small s is standard deviation. If you do small s squared, that's the variance. Remember, standard deviation squared is the variance. Population, so that's for the sample. The s's are for sample. Population is the curly Q guy. Little curly Q guy is the standard deviation for the population. The little curly Q guy squared of standard deviation, it's the variance. So S squared is the variance for sample. Little curly Q guy squared is the variance for population. I'm not going to get into this a lot, so you don't need to know this. We'll talk about this later. It's much more important for inferential statistics. All I'll say about this is remember when I told you that why do we use n for a mean? And why do we use n minus 1 for standard deviation? This is why. This is the mathematical reason why. You don't need to know this slide now. We'll talk about it more when we get into inferential statistics, so you can skip this slide. Don't worry if you don't quite get it. Just know that n minus 1 helps correct the number for standard deviation. That's all you need to know about that. And so this I'm not so worried about. We talked about this already. So the graphing part, you can go look at the means and the medians that we talked about in terms of graphing. And now we have two big pieces of information for descriptive statistics. Now we've talked about central tendencies and we've talked about variability. And remember that for distributions that are basically normal distributions, we're going to use the averages. The averages are the mean and the standard deviation. So typically when we do research, we typically have distributions that are fairly normal. So I have presentations here about using those things, the mean and the standard deviation, the averages. So when we write it up, we want to give the mean and standard deviations for groups if we're looking at it. So if we're looking at the intelligence IQ scores, men versus women, we want to give the mean for men and the standard deviation for men, and the mean for women and the standard deviation for women. So that's just an example of how you might write that up in a sentence. There's various ways of writing it up. That's just an example. And again, what I'll say is in a lot of this class, we're just going to take a little bite of things that we're going to have a whole meal later. So this is a little bit of something that we're going to do a lot more later. So if this is clicking, that's great. If this is not clicking, don't panic. We're going to be doing it ad nauseum. That's probably a good term for you to learn. Ad nauseum means until we puke. So we will puke a lot with this later. So if you aren't puking now, that's fine. That's a weird metaphor, but I went with it anyway. So here's another example of using mean and standard deviation. So if we were looking at, for example, the variable of education, so you might just describe our whole sample. So our sample as whole was well educated. The mean number of years in school was 17.21 with a standard deviation of 2.34. By the way, I sort of mentioned it earlier, but I'll just sort of say it now. Why do we do standard deviation? Because variance is also an average. Well, the standard deviation puts it into the units that we're studying. So here, the standard deviation is in years for the second example. For the first example, that standard deviation is in terms of points, in terms of the IQ test. So the nice thing about taking the standard deviation versus the variance is it puts it into the units that we're studying. So the first one is IQ points. The second one is years. And then the same data that are here, you can also just report it this way. So again, this is just a little bite of what we're going to be doing a lot more later. So we want to give the mean and standard deviations about the people. We're talking about whether it's the whole sample, or if we're comparing two groups, we're going to give a mean and standard deviation for both groups, men and women. So we're using these to describe either the whole sample or for groups in our sample. And that's pretty much it. This is just a highlight of what we're going to be talking about in the lab. So we can run SPSS and generate these numbers. I will talk about this more specifically in the video about the lab. And fairly soon, I'm going to put up the homework. And this is wrong. It's homework 3, because we had a nice little easy homework, which was your introduction. So homework 3 will be on Canvas soon. And homework 3 will have you do central tendency and variability. And lab number 2 will also have you do central tendency and variability. And I will make a video about the lab and explain SPSS more in that video. So that's it for this lecture, and I think that's not too bad. So lecture 3 and 4 were pretty easy. So I will talk to you in the next lecture.